Okay, so looking at the notes you got in front of you, volume of revolution. So what we're going to do is we're going to take some region and rotate it about an axis. Just spin it around. So what we're looking at right now to get started, region rotated about the x-axis. Well, the first region is y equals x squared, y equals 0, x equal 3. So we get this region right here. We're going to rotate about the x-axis. That's that little curly Q there. So it's going to go around and around and around and around. Sort of something looking like this. If we would rotate this around, same region by the way, okay, this is what that area would look like. I know you can't see the bottom, but that's so it looks like that down here. Now that might look more like two-dimensional, but let's see what happens when you rotate or revolve one of those around. You see how you get that circle, that little disc, and of course if we bring it out to here, it's a little bit bigger. Bring it in closer, it's smaller. We'll bring it out so we can see that a little better again. Here, let me clean it up now. One more time. So rotating, and we're rotating all those radii around. So what's the area, or a rectangle, what's the area of a circle? Exactly. So we got to find out what that radius is, and we'll go from there. Okay, so here's that, back to this figure. What's that radius? From x squared, y equals x squared, to the x-axis. Plug that into our formula, pi r squared. That's the area of one circle. When we multiply by dx, we get the volume of one little disk. Area to base times the height, the thickness of it. Think about like if you would take a piece of paper and stamp out a circle. Cut a circle out of it. It looks like it's an area, but we know there's a volume. There's a little itty bitty thickness to it. And I'm going to take all those little itty bitty rectangles, or actually discs, circles, add them all up from 0 to 3. And so, of course, when we go ahead and do that, we get a definite integral. Simplify first. Integrate. Fundamental theorem. Done. I'll let you fill in the blanks on your own calculations later to verify. But anyways, when we rotate stuff, volumes of revolution, for the ones we need, there's a different route, but we'll look at that much, much later. It's just a cross section, it's a circle, so area equals pi r squared. So our integrand here is going to look like pi r squared, or some version of that, some way, shape, form, or another. It's going to be the area of a circle. Period. That's all we're trying to think of. What's that radius? What's the radii? What's the radius of this circle? What's the radius of this circle? That's all we're looking at all this. Okay? So, let's go to the next one. Bounded by the y equals square root of x plus 1, y equals 0, x equals 0, x equals 4. So, square root of x plus 1, y equals 0, x equals 0, x equals 4. It's always a good idea to draw this. How accurate? We just need a visualization, or else it's going to be tough for you to try to figure out, without drawing it, without sketching it, what that radius is. Because again, we're putting it into the pi r squared. Okay, so let's go to this one here. There's your x squared plus 1 from 0 to 4. Okay, now this time we get, if I revolve all of them, so notice it's still that circle all across, either there, in here, over here, up there. Even though it doesn't go to a single point, that's okay. So this sort of looks like, oh, could be a bowl, could be a basket, or maybe like almost sort of like a shield of some sort. Or drill a hole through it and it's a bullet weight for fishing. Okay, so we got to find the volume of that. But what do we really have? Is we're finding the area of one of these disks and going to integrate it. So what's that? Radius from the curve f of x, square root of x plus 1, to the x-axis. So that's the radius. Plug it in. No, I'm not going to try u sub because I don't have the derivative. Yeah, the derivative of the square root of x plus 1 anyplace else in the radicand. In the integrand. Radical got me thinking about that. So actually, nicest way is just to go ahead and simplify. That's what we did. Yes, you can multiply them together. Square root of x plus 1 times square root of x plus 1, or just use the formula. Square the first, square the second, multiply those two together, times 2. So there's your new integrand, simplified. Integrate, find your antiderivative. Now use fundamental theorem. Again, you could drag the pi along in both places, but we could just factor that out in front right here. So we get this. This is a very common kind of answers. Well, when you think about it, since we're starting from the area of a circle, pi r squared, our answers probably will have pi in there somewhere. Okay? So you have to try these. So next time we meet, try some of those off to practice. Some of those with the regions already drawn. What's the radius? Plug it into pi r squared. Integrate from where to where. Okay? Again, only way you're going to get good with this is by working and trying them. Do some.